not racist, actually. That's
What?
just mean.
What is it? Is it because I'm Burmese? Is that why?
Because you're mean.
Oh my gosh. I hate you. I don't want to be alone.
You're behind.
That was not the song I was going for. Did you read the thing for Alicia? For what's it called? Amsterdam. Oh yeah. Where did you go? Oh.
I'm surprised that you didn't do that before you left.
Hey, good morning.
Good morning.
Good morning.
So, we are going to continue talking about the need to be more there today. We're going to give you a better understanding of what we mean by weakness among acids. And then at the end of class, we will go back and look at the test. Okay, this is your scores. Last class, those of you who chose to today will take the last 15, 20 minutes, and I'll actually ask you to go over some things and answer some questions. Okay? All right, so kind of debate on what is the best way to do this. Does anyone have any questions about the homework that you had last night? I know students can't see me, so I know they exist. Kind of debate on the best strategy to answer this question. Should we go to today's activity or should we write it? And I'm actually let's start with today's activity. Bring that, come back to that, and kind of wrap things up. Okay? So, right now, hold on to those assignments. And let's go ahead and start something slightly different. Okay, give you a little bit of history. This activity that we're going to start out with used to be a lab that we did. Unfortunately, it did not always work like it should have, and so I think in some cases we were causing more harm than good. So we modified things in that now give you the data and just really have you do the calculations based on the data that's correct. And the data that's a bit inaccurate. Okay, so let me pass this out. Tables don't like each other.
Thank you.
Thank you.
I like citric acid.
Okay, so this is the strong versus weak acid labs. Okay, and as the name implies, this will give you a better understanding of what we mean by a strong versus a weak acid. We've already talked a little bit about strong, very little. No, actually, we did talk about weak in a little bit with math in class. But what you will do to complete this activity is start out by completing the table. Okay? And so it gives you pH values for these different concentrations of solutions of nitric acid, which is another of the strong acids. And then on the second page, it gives you the information for acetic acid, or the pH values for acetic acid. Okay? So, again, just make sure that everyone is clear. What do we mean by an acid? What is the definition of an acid?
This is already within the direction.
Okay. So I like everything you said with that D word. So acids ionize, bases dissociate. Okay? But yeah, so an acid is defined as a substance that releases hydrogen ions when placed into an aqueous solution, basically when placed in water. So we oftentimes will use the general reaction or equation of HA, where A is the rest of the molecule, and H being that hydrogen is released. And so when placed in water, it becomes H plus and A minus. Okay, and like I said, A minus. Your A depends on what acid you're talking about. And so, in the case of nitric acid, when we place that in water, then our products would be some mumblings.
H plus.
Exactly. Okay. And so this is the strong acid you're going to be working with. And then your weak acid is acetic acid. Okay. So similarly, the products of the ionization of acetic acid are OH. These are acid. These are both acids. Acids can release bases. H plus and the acetate ion. Inorganic is different. So this would be your inorganic acid. This would be your organic acid. Inorganic acids have a little structure that look like that. Okay, which we've seen before when we did little structures. Okay, and so because it's typically written from left to right, the H ends up here. Okay, and in an organic acid, inorganics are the same way. But it's, again, it's basically the way the molecules are arranged that dictate how the structure is written. Okay, so, again, we know that pH is equal to negative log of the concentration of hydrogen ions. And so the concentration of the hydrogen ion is 10 negative. Okay? So, and what do we know about when an acid dissociates or ionizes? I'm going to trap myself. So similar to what happens with water, which also ionizes to a very small extent. Okay, so we've got our water molecule, we lose our hydrogen. So what do we know about the other product, our A minus? Is that in the case of water, it's OH. In the case of nitric acid, it's NO3 minus. But what do we know about those two substances? This part would be a minus, exactly. So that's where the NO3 minus comes from, and the CH3COO minus. But what else do we know about this as we do those calculations? What do we need to remember about these and their calculations? Okay, so I have one water molecule, right? That one water molecule ionizes to give me one hydrogen ion and one hydroxide ion. So in this case of our other acids, for every hydrogen ion we release one of the A minus, whatever that may be. Okay? Because that's going to be very important as you do the calculations for the acetic acid. So for every hydrogen ion that we release one acetate ion as well. Okay? And so, in this table, the first table on the first page, you want to identify or calculate the hydrogen ion concentrations. And from that, then determine the NO3 minus concentration, which we just talked about. Then there's a couple of questions at the bottom. You want to take a look at those, make sure you can answer them. Then, on the second page, you want to, you're going to again calculate the hydrogen ion concentration based on pH. You're going to determine the concentration of the acetate based on the hydrogen ion concentration. And then from there, you're going to figure out how much of the acid that you have. Okay? So I'm not thinking about this in terms of chemistry, but thinking about it in terms of math. How would you go about figuring out how much acetic acid that you have based on your concentrations of A plus and CH3COO minus? if you have a beaker, and in that beaker, you have your solution of acetic acid. And if those two circles represent each molecule of acetic acid, and in that beaker, some of the acetic acid molecules, bless you, break apart into hydrogen ions and acetate ions, but not all of them do. Then how would you figure out how much intact acid, bless you again, you have once your system reaches equilibrium? Okay? As Emily said, you simply take the original amount, so those 8 molecules that I had drawn, and subtract out the ones that break apart. Okay? So based on your pH, which tells you how much H plus ion you have, and the fact that we've given you the concentration of the original acetic acid before anything broke apart, you can figure out how much is left. Make sense? Okay, so give it a shot. I'll let you work through it for a little bit, and then we'll come back and it also asks you to calculate or to generate the equilibrium expression, and then to calculate the Ka value. Okay, so let's see if you can do that.
Okay. So how do we do this?
Okay.
Is there anyone else that needed to turn in the lab?
What's the last day was on the one that we did 2 classes ago, right?
I don't know.
We're working together, right?
Yeah, sort of. For the H plus, did you guys get one?
I got 0.1.
Oh.
Do you know how to do this? Do you know how to do this column?
-1.
Wait, it's a negative log, right?
Okay.
How did she do it?
She just used the equation.
I know that pH equals negative log.
Oh, okay. Yeah. Thank you.
How do you find the thing from there?
Okay, so write out the equilibrium expression. Get all your data. We're going to go over that. Just hold tight. Once we get through this, we'll go back and study that.
The consultation of the H plus and this kind of
Do you guys know how to do the third column?
No. I just doing out the first one for it, but I'm not sure how.
Wouldn't it be the same thing because ratios?
So I'm getting 0 for all.
No.
I don't know even.
You all have the concentration of hydrogen ions, and this is the whole thing. You should just subtract them to get this. They're separate.
What?
But what's just 0 for each?
Use decimals, please. Use fractions.
But this equals that.
That's not what you're doing. You're taking the negative log of your pH. It's not 1 over 10.
The negative log of my pH.
Yes.
No, you're
I
doing
mean, you're
10 to the
taking
negative.
to the negative, right.
And that
Don't
equals
use
this.
it- But don't, you're gonna have a hard time trying to use a fraction. Please use a decimal. I'm sorry? No. So again, if this is your hydrogen and this is represents the NO3. Okay, so this is your intact nitric acid. Okay, for every H plus that you break off, how many NO3s do we have? Exactly. So the concentration of this is going to be the same as the concentration of that. Because the two of those make up one of those.
So column 3 is equal to column 2.
Yes, because of ratios.
Does that make sense, Glenn?
Oh, yeah. You subtract like we don't actually know because that's like the 42 separate, so each one has that concentration. So you just see that one, you subtract the total concentration from
Don't we have to answer that question? If it completely ionizes, does that mean everything breaks apart fully? Or instead of having like 0.5 or something?
For one molecule of acid, we're going to 2 of them. So you have that many add the two together. Two of them make up one molecule.
Why is that pattern?
What?
Why is
Don't
there?
get number
Because of
crazy
the
either,
ratios.
people.
What?
Pay attention to sig figs, please.
What'd you say?
Because
And
of
like,
the ratios. It's the ratio of this to this in each molecule is 1H for one. There's 1H for every NO3.
Wouldn't this just be this?
I'm not there yet. Where?
Wouldn't ask for this, wouldn't it just be this? I feel like it would be
That
this.
feels too simple, but it also.
I feel like it's supposed to be these added together. I don't know. Like this is the reactant, right? So that would be. What is this, product or reactant?
It looks like it's the reactant.
Why
It
did
can
the
go either
ratios
way.
change?
Because there's still 1H for every CH3COO.
Right, so that means that it should be equal. So
Yeah.
it should be 1, not 5.
What are you talking about?
It should equal this, not that.
We're not writing down the ratios, we're writing down the concentration. I'm just saying it.
But the concentration is 1 mole.
No, that's the molarity. That's
But all the concentrations are molarities.
after they break apart.
Right.
So, no, it's this.
What is this supposed to equal?
KA probably.
But then you have to write the K.
Yeah, so you just calculate it out using those values.
How do you calculate Ka again?
You have to write out the expression and then you fill in all like the stuff that you just calculated. So that's like Ka equals the products of the reactants.
Okay. Oh, I thought that was KEQ.
I don't know. Sometimes it's K, sometimes it's Ke, sometimes it's random stuff.
How did you find CH3COOH?
Huh?
How did you find the...
I didn't. I don't know what they mean by that. Like, does that mean it doesn't completely ionize? Is that what they're trying to say? Or,
That would make sense because before it was equal to the thing, whereas now it's not.
yeah.
Because this is a 1-to-1 ratio, right? So they
Yeah.
should be equal.
Yeah.
Oh yeah, if we think of how
The only slight difference is going to be because of the K.
Shouldn't the K expression and value be the same for all of them?
Because you rounded.
Not the value, but the expression. Because when you fill in the concentration, I think the concentration of the CH3 whatever is going to be different because of the molarities. But I think this is just this. Because don't the brackets mean like the concentration? And then, so shouldn't they be the same?
The concentration of this.
Yeah, it's the same as that.
Why would it be?
Because the brackets mean like concentration of,
Yeah.
and so this is the same.
Wouldn't
as
they all be 0? Because if you break it apart, then there won't be any left.
So, wouldn't this be?
I'm not sure.
I guess.
The thing is that it might not completely deionize. There still might be some of this left. That's why.
So what's the equation for that?
I don't know.
so right now, this is the only time you're allowed to without even.
When you get there, can you tell me what you got for your Ka value? Because it looks like a huge number.
Taking care of us. Got my life somewhere. What did you get for the Ka value for the first one?
I didn't.
Oh. Dwayne, what did you get for the Ka value for the first one?
Wait.
62,500.
Oh, you put the product over. You put the reactant over the product. It's the other way around. So that might be why you're getting such a large value.
Yeah, I got .0000025.
Yeah, that's probably what it should be then. Dang it, Wayne.
I asked you. You said
Should
it
it
was
be
correct.
1.6 to the...
I didn't understand what you were saying, so I was just like,
Wouldn't it be 1.6 times 10 to the negative 5?
For the Ka value?
besides, don't trust me.
How did you get that?
You do 0.004 squared divided by 1.
Why?
You do this times this divided by this.
Yes, and how did that give you that?
Because this times this.
Yes.
Well, first of all, I got 4 because to get that you need 10 to the negative 2.37.
Wait, what did you get? How'd you get 4?
Because I did 10 to the negative 2.37.
You get 1 point.
Oh, I got what you got, 0.004. But I just set the 4 because yours is a 5, and that's the number.
Oh, yeah, I didn't see the 2. I saw the 6 and I rounded.
But then you do that squared divided by 1. And then that's basically going to be 1.6 times 10 to the negative 5.
What did you get for number 1?
Hang on. I rounded wrong. That's what I say.
We'll spread that through together, Dwayne.
Yeah, .0000016.
0.00016.
0.00016.
Just do 1.6 times 10 to the negative 5.
But that wouldn't be 1.0 times 10 to the negative 4 because you have 3 significant figures. Wouldn't that mean you need 3 significant figures for the last one?
Give me some more digits than that. You've only got one sig fig here. I gave you 3. Jen, so put those numbers.
You can't do that because the 0 is before the 1, not after the 6.
The 0 is before the 1 and that's it.
Size. I did the same thing.
You didn't get the
All concentration.
It should be 427 then, right?
Yeah.
and then 135 for the next one.
And then for the after one, it's like 0.00417 or
I got 4.17.
Same thing. I think.
No, it'd be 1.690 times 10 to the negative 5.
Yeah. I just wrote it out. What?
No, I just keep mixing up like these aren't counted, and then I keep like, no, they're counted. Yeah, I'm sorry, I'm just like, they don't count unless there's a number.
You always seem small.
So then this is
You didn't, for the first one, did you get like 1.823 to like 10 to the negative 5?
No.
How?
Show me your calculator.
Oh.
I don't understand what you mean.
So you should not do that.
Because she has just as many zeros as I did. I just wrote it as a scientific notation.
Right, but you don't have as many, did you use .004 in your calculation? That's why your number is off. You only gave me one sig figure.
I did get that. I just, my calculator didn't show me that many digits.
For your pH.
That's it.
I mean, for your hydrogen ion concentration.
That's it.
No, it isn't. It's .427. .00427.
But there's only 3 significant figures.
Right, and you've only given me one. Those zeros that are in front are not significant. You need to figure out the other ones as well.
What did you get for the second one? Did you get 182 times 10 to the negative 5?
Yeah.
Did you get the same thing for all of the carrier values?
No.
The third one's different.
Okay.
Did you get the same?
I am just on the second one.
Okay.
The second one's the same?
I think
Three of them should be
That's
the
not what
same.
my calculator showed me.
Then you did something wrong.
.00141.
What did I do wrong?
My calculator is rounding weird. It's not my fault.
Negative 3.38. 4.
Yeah, I got something different from the last one. Okay.
Let me see.
No.
Oh, for the third one you got something different. Yeah, okay.
No.
Times
Why did you want to see it?
negative.
Because I thought you said you got something different for the second one, and I'm like, it might be your calculator rounding wrong, because my calculator is rounding wrong.
Divided by 0.2. Nope, I'm still getting
Okay, so I think everyone has pretty much finished these calculations. So let's take a look and see what information we can glean from doing this activity. First of all, whenever you come across a equilibrium reaction, it's always good to write the equilibrium expression. Okay, so for both of our ionization reactions, our equilibrium expressions will look like what? The equilibrium expression for the ionization of nitric acid. For nitric acid. Finish my part here. Now to understand what's going on here, let's use what I like to call, I didn't come up with this, but we oftentimes need to list the ICE table. ICE. And this ICE table stands for so initial, the concentrations of your reactants and products before the reaction takes place. Okay? C represents the change, what's going on as your system gets to equilibrium, and then equilibrium is the concentrations of your reactants and products once your system is in equilibrium. Okay? So, in most cases, now there are exceptions, when you start, before you start a reaction, before the reaction takes place, how much product are you going to have? None. Exactly. before the reaction takes place, how do you make a product? The reaction hasn't done anything. So that is the case here. So initially, there is no product, and we'll just use the first concentration. So we have 0.100 molar nitric acid. Okay? And then some change takes place. Okay? In this case, we know, actually we're going to jump down a step. Okay? But this is for a known, and then we'll kind of take it back and set it up when we don't know all of the information. Okay? So at equilibrium, we have the concentrations that you determine from the pH. Okay? And so for the 0.1 molar solution of nitric acid, where the pH is 1, the concentration of H plus is 0.1. Taylor, can you shut your laptop and everyone else too? And we also know that because the concentration of H plus is 0.1, the concentration of NO3 minus is also 0.1. Okay? That tells us that the change that H plus and nitric acid underwent was going from 0 to 0.1. So that change is 0.1, an increase of 0.1 mole. Okay? Because the only way we can get from 0 to 0.1 is to increase by 0.1. Right? And so if our products increase by 0.1, what had to happen to our reactant? What's that? It had to decrease, because that 0.1 molar had to come from somewhere. Okay? It doesn't just come out of thin air. And so the same amount that our products increased, our reactant decreased. Right? And so in our angst table, to get E, we simply add I and C together. So 0.1 minus 0.1 is 0. So when this system is at equilibrium, we have 0.1 molar of both of our products, meaning we have no more of our reactant method. Now you follow, not just numerically, but conceptually. Does it make sense? Okay, this is the time to say, no, I don't get it, I don't understand. Because if you don't get it now, you're going to be completely lost as we move on.
So if there's 0 reactants, then how is it equilibrium?
It's truly not an equilibrium. Okay, and I'm coming to that. Okay, so strong acids don't exist in equilibrium. But we have to kind of come from that angle so that you better understand the weak acid. Okay. Big question. Okay, and so as we then calculate the Ka, which again is simply a ratio of the products to the reactants. In the case of nitric acid, Ka is found by multiplying the concentration at equilibrium of the products divided by the concentration of the reactants. And so the solution to that is undefined. Okay, that's why strong acids don't have Ka value, because they do not exist in equilibrium. Ka is simply that ratio when your system is at equilibrium. Makes sense? Everyone get it, not only numerically, but conceptually. Okay. That's why the table on the first page is so much smaller than the table on the second page. They didn't even ask you to calculate Ka value, because it doesn't exist. Okay? But acetic acid, which is a weak acid, if we do a similar ice table, first of all, let's do our Ka expression. Heating. You need the Ka expression for acetic acid.
H plus CH3COO over acetic acid.
Thank you. Okay. So, similar to the nitric acid, the initial concentration of acetic acid is 0.1 molar. Actually, the first one we used was 1 molar, but I'm going to use 0.1 molar. Okay? And at 0.1 molar, that solution has a pH of 2.87. And so based on that pH, the concentration of H plus is
0.00125.
0.00125.
135.
1.
3.
Oh, I'm sorry, I didn't hear that. 3.125, you said?
1.135. Okay.
One more time.
0.00135.
Oh, okay. I had 125, I should have been 1.3. Sorry, we get old hearings when it first rings together. Okay. But initially, our concentration of H plus and CH3COO minus is initially, Trent, 0. This may seem very simplistic, but I guarantee you there's somebody in here that will leave this classroom today and realize they don't get it as well as they think they do. Okay? Okay. Which tells us that our concentration of acetate is also 1.35 times 10 to the minus 3. Again, our change for our products would then be means the change for our original acid must be equilibrium, the concentration for 0.1 molar acetic acid is 0.09. And in this case, we can in fact use our equilibrium expression, plug in our values. And we should get something in the line of 1.8 times 10 to the minus 5. Okay, 1.8. Someone did this calculation with these numbers and got 1.8 what? Yes. Yeah, they should all be normal. Thank you. Yes. Yes, you can.
How would the change in the reaction?
We'll come to that in just a moment. Okay, good question. Okay. And so, as you do the same calculations for the 1 molar and the 0.01 molar, the Ka value should be the same. It's a constant. Okay, it is not dependent upon the actual concentrations, but more the temperature and then the pressure. So those external factors. Okay, so this K value is truly a constant based solely on the substance. Okay? Questions about this? All right, so you want to complete the rest of these the post-lab questions for Tuesday. But I want to go back to
Yeah.
How is your nothing? show you how this, listen up please, show you how this modifies Is this the side effect of all those pills you took yesterday?
No, this is from the pills not working.
What?
This is from the pills not working.
I can't hear you.
This is from the pills not working well enough.
Ouch. You should probably go to the nurse. Because your eye is like really red.
Really?
Like your actual eye itself. Might be because you kept putting like the tissue in it. But it's like red. Do you have any eye drops?
Nope.
Okay. We're trying to figure out what we got, what we went wrong here.
So, a question was asked about, listen up please. Question was asked, what happens when the values aren't equal? So it's not a one-to-one to one type of stoichiometric relationship. Okay? So, here we have the reaction of nitrogen gas or hydrogen gas giving us ammonia gas. Okay. So, if given that reaction, what would be the first thing that you would do? You need to balance it.
The 3 as a coefficient of H2 and 2 as a coefficient of
And so that translates into an equilibrium expression that would be
NH comes from NH3 squared divided by concentration of nitrogen gas minus the concentration of hydrogen gas used.
Yes. Okay. And so our problem says that we start out with 3 moles or 3 molar. So we're starting out with 3 moles of N2 gas and 1 mole yes, in a 1 liter container or in a 1 liter vessel. Okay? And we want to calculate the we end up with 0.663 moles of H2 at equilibrium. Okay? Because this vessel, a reaction vessel, is 1 liter, then our moles, in terms of molarity, would be the same with the values of it. Okay? Because all we're doing is taking our number of moles and dividing that by 1 liter. Okay? So our moles can now be written as molarity. That's you. Okay? So, we've got part of our table filled out. We want to finish completing it so we can then calculate our Ka value. So, question or
So all of the three values that you, are those given in the problem?
Those three are given to you in the problem, yes.
Alright, I think I know, like, how to start.
Okay?
Could you possibly, I think you could use lower ratios to find the initial amount of product that you made. Or no, initial product is 0.
Thank you. So when you look at initial, we're always talking about before our reaction takes place. Okay? And so unless the problem tells you that you're actually starting with some product already, we always assume the amount of product to be 0. Yes. Okay, before we do that, however, let's do this. What do we know is going to happen when, in very general terms, what do we know is going to happen in our change portion of our ice table? And, exactly, okay? So our reactants are going to decrease in concentration while our product is being formed and will increase, okay? But in this case, where all of the coefficients are 1, though, that has to be taken into consideration as well, okay? So what would be recommended is, let's say we don't know this value, okay? But we're given enough information to be able to calculate it. So we're given the Ka value. We can then calculate what those values are, okay? And so for just a moment, we'll ignore this and we'll put this in more general terms, okay? And so looking at our stoichiometric ratios, what in terms of X will we be gaining and or losing in our reaction?
So you'd be, for the change in N2, you'll be losing, say, X.
Okay, so if one of our coefficients is 1, then that's typically the one that we want to set equal to X. Okay, be it plus X or minus X. Okay, which means the change for H2 is going to be minus 3X. And the H3 is plus 2X. Does everybody see that? Okay, all I did was took our X value and multiply that by the stoichiometric coefficient. Okay? And so now we know we basically have an equation. If I plus C equals E, then 1 minus 3x equals 0.663. Okay?
You don't have to do anything with the living reactant.
Yeah. Actually, it all gets kind of factored in here. Okay? So, solving for x, is equal to 3x, and x is close to 1 something. Is the next digit less than 5? So 0.112. And so if x is equal to 0.112, then the equilibrium concentration for N2 would be
224. Oh, read that. 2.88.
Using the correct number of sitting figs, and 2.89. And for the amount of NH3,
Also the change I got for industry, I got negative 0.225. So,
say that again.
so I did 0.112 times 2 scale change,
Right.
which was was 20.225.
Okay. So that would be 0 plus 0.225. Okay. And so our equilibrium expression would then, or our equilibrium equation would be 0.225 squared over 2.89 times 0.663. Okay, does everyone see how I got that? Because I noticed several people open laptops again, aren't paying attention. It's getting a little bit frustrating. So, as you are answering equilibrium type questions using the ice tape, in some cases, when you're dealing with a weak acid, you'll be given pH, where you can then calculate the H plus concentration. In some cases, you'll be asked to calculate pH, where you'll have to use the variable. And then instead of having actual numbers, you would use in your equation 3.00 minus x, 1.00 minus 3x, and 2x. Okay, so everyone see where that came from. So we took I and E and added them together. Okay, and if you're given a Ka value, then you simply plug those variables in to solve for x. Yes?
So can you tell when it's in strong?
Absolutely. How would you be able to distinguish a weak from a strong acid using Ka values?
If there's not K value, there's no.
If it doesn't have a K value, or if there isn't any reference to a Ka value, you know it's strong. And you know whatever the concentration of the acid is the concentration of your hydrogen ions. So you can calculate the pH from that. Okay? Keep in mind that for something like sulfuric acid that releases 2 hydrogens, you have to double the concentration. And just like we had to do in that previous worksheet. Vincent, has your question now been answered from
Oh, yeah.
the other 7 on the worksheet? All right.
Zoe, seriously? Seriously? You're doing math homework in my class? Please put that away and don't let me ever see it again.
Thank you. Yeah. You have to give me the other one. So, where did we even go wrong on the third part that we got a different answer?
It's because we didn't do that.
So, for
You mean the third column?
We went off this.
What?
What did,
For Tuesday, you need to have, listen up please,
Where'd you get mine?
the strong versus weak acid that we just worked on,
Where'd you get mine?
completed, all the post-lab questions.
That's 4.
The pH and equilibrium sheet that I
got
gave you
2.
last class, that you now should have everything you need to complete. So question 7 was an ice table type problem. Okay, so you should be able to
You
now
guys got different
use the
answers?
ice table to get that
For
done.
the third column?
And then the sheet that I just turned or passed out, you need to have that complete as well. We will be collecting one of them. I'm not telling you which one. Okay?
Okay.
you got this, right? It's because we went off with
But
writing
our answers
this
are correct, right?
as this instead of doing the ice.
For this.
No, these are supposed to be all be the same. We don't know why.
So
No,
like this.
2 of them are supposed to be the
Try to
same.
make this,
No,
which give us this new
She said that the K value should remain constant.
instead of one.
No, just for 2. So that thing is like the equilibrium. And not just whatever value you get. Okay, that's confusing. Good thing. I get it now, but I'm like, why would you write the expression? Yes. Alright. Thanks, Jane.
You ready for that?
But the KA expressions are still the same.
Yeah, they should be all the same.
Okay.
Amy Costello walking to the store. I think it's after 50.
But our third column's wrong, that's why.
Yeah. So are we changing this column to what we do with
You
the
don't
ice
change
table?
it.
No?
You, like, all this stuff is right. It's just that we used this value for this when you're supposed to use whatever value you get from using the ice table.
Okay, thank you.
Yeah.
I can't Still not possible. Think of anything. I get the same answer though.
Wait, what? Here. What'd you do?
For the second column, for the second row.
Oh, did you guys get
What are you
1.82
doing?
times 10 to the negative 5?
What?
Did you guys, for the last column, get 1.82 times 10 to the negative 5?
You're supposed to get 1.84.
That's what I got originally.
For all of them?
Yes. Times 10 to the negative 5.
And it was because... Okay.
You okay, Zach? There was an example up on the board, but if not, you can look at my notebook.
Who?
What?
What are you talking?
Oh, I'm talking to Erin. And your calculator is buried under a bajillion different things.
Oh no. Maybe passed out. Welcome to the store.
Why'd you think some of the
For number 5, is it because one is strong and one is weak? Or is it like something
I'm not there
else?
So number 5, I thought it was because the concentration of hydrogen is different in different assays. Like for example, the one we're working on in part